Welcome to another vBrownBag Build Day video. This is the Datrium Build Day, and I'm joined now by Mr. Devin Hamilton. Welcome.
Thank you very much. It's awesome to be here. I really appreciate you guys coming in.
Hey, it's a lot of fun. What is it that you do? What would you say you do?
What do I do at Datrium? I've been at Datrium about 2.5 years as the Director of Systems Engineering. That's a broad title to say that I go out and I talk to customers a lot. I have built the systems engineering team here, and I spend a lot of time working with our product management group and expressing the needs of what our partner community wants to put out there to the customers. And so it's a lot of jobs. It's a good time.
In this video, we're going to have a look at the basics of the architecture of the Datrium products. Naturally, we're going to dig under the covers and poke around and find some things in later videos.
Sure.
But this one is the overview, particularly for those who have not previously been briefed on what the Datrium architecture is. So I'll hand over and let's head straight in.
You bet. I think for a point of reference, it's good to understand where open convergence came from as a terminology and what it means to us. And so to do that, we really do leverage technologies that have come before us. So convergence really got its start in SAN and having a capability to put controllers and performance into a box at the end of a wire. And then functions of copy data management and other things that increase that intelligence on that platform. You go beyond that and you're in the realm of hyperconverged. And hyperconverged really focuses on the easy button approach and putting caching and intelligent I/O workloads all within the same framework. Open converged evolves beyond that to say, hey, look, the customer environment already had an ample amount of x86 compute in play. That cache is really a commodity available resource, that it's plentiful, it's not very expensive. Why not utilize those two things as existing infrastructure and determine a way to make a betterment out of those or further enhance them for greater use? And so Open Converged brings to the table something that looks a lot more like software defined, that we put software onto those existing hosts and do something with all those compute IOs that are available to us. But because of the customer ecosystem really driving a direction for us, we recognized that we needed to have a full turnkey solution that included both the compute aspect as well as the capacity aspect. And yet those things are decoupled or disaggregated in our solution. So Open Converged is really kind of the culmination of all the greatest things that SAN ever provided and all the greatest things that HCI ever provided, but none of their pitfalls.
So learning from the mistakes of others to build something even better.
Very much so. Paying for the sins of our past is the way we think of it. So kind of walking through that a little bit, I'll express some of the things that we're doing in terms of what the customers feed back to us. And that really comes down to what we do differently and what we do similar to what they're used to. The intent of our technology is to focus on what the virtual machine server application stack is doing and really be able to also handle within the same set of solutions all of the data protection aspects of this as well. So really when you look at a Datrium stack, the Open Convergence is focusing on the server, the compute, the I/O pathway, the application acceleration, the intelligent caching, but also the protection of all of that data. And there are a couple of things to consider there in terms of snapshot methodologies, replication for disaster recovery, and so on. We'll get into that. Really, at the end of the day, Datrium represents a turnkey solution that is agile to drop into a customer's existing environment and provide resources that enhance it, but also use some of the stuff that they had there already. We call it DVX. And I want to spend a minute just expressing what that name means. DVX is basically meaning Distributed Virtual X, where X is cool and comes great after DV. And it really denotes, at a technological level, kind of a placeholder for many of the things that we do in software that are germane to providing a high-speed experience for the end-user customer, providing distribution of metadata workloads, but unlike HCI, not distributing a write workload across the cluster. And we'll talk about that and kind of what that isolation looks like. We're an engineering company, though, so there's some things that have come out of just hallway conversations and backroom and things like that that are names that end up sticking, and that's kind of cool.
And there's an allusion to ESX and GSX
exactly.
in the X
exactly.
on the end.
Exactly, and Elastic Sky, yeah, exactly.
Yeah, so really DV should not stand for anything to do with the technology. You've got to find something else for DV to
stand really, for it to be authentic, yeah, absolutely. In terms of terminology, and let's kind of focus on that, I find that the customers benefit when we express some of what we're doing here. And basically, in Datrium speak, there are compute nodes, and a compute node would equate to an ESX host. Now, that doesn't have to be just ESX. We support multiple hypervisors now. This could also be persistent containers in bare metal Linux. This could be KVM. But ESX is, by and large, the majority environment that we install into today. A data node, of course, is an off-host appliance, and that is an appliance that we are selling. We also sell a compute node, or we can use the customer's ESX hosts as compute nodes. Really, in terms of host flash, we can support any kind of architecture that the customer is interested in using. So that could be SSD, NVMe, it could be PCI-based. If there's a performance concern and they really want to kind of hot dog the environment, we've been supporting NVMe for about 2.5 years, and our earliest implementations were over 2 years ago.
And fundamentally, that's any flash device that's supported by the operating system on the compute node.
Yeah, exactly.
Could be supported.
It's worth noting that basically if VMware can see it, so can we. And that gives us a lot of latitude into what we can leverage from the consumer's choice set, that they can go out there and grab really any commodity flash from their server vendor or from their favorite reseller partner or other sources. The notion is that we are not a flash vendor. They're not buying flash from us. If they're buying our compute nodes, they are equipped with flash. That's basically the same stuff that you would get from Dell, as an example.
Yeah.
So rounding out the terminology discussion, a third-party compute node, that references what a customer already has, versus a DVX compute node, that would be one that they're buying from us. And really, that kind of rounds out all the pieces and parts of the architecture on the whole. At that point, you just kind of think through where these things plug in. And so if you look at a Datrium environment deployed at scale, what you'd find is that I can scale 128 compute nodes to as many as 10 data nodes in a scale-out cluster. That scale-out cluster is erasure coded. So there is a distribution of data as writes occur to that underlying pool of storage, and that becomes the master copy. There is no distributed writes across the host compute cluster. Therefore, I don't have any resiliency concerns or any redundancy or, in fact, any significant noisy neighbor problems, because I'm isolating I/O really in a southbound direction to this data node. This has given us numerous advantages. And when we look at how this deploys, certainly compared to or contrast against HCI, the first thing that we see feedback on is that we can distribute any kind of workload across the cluster and never have one workload hamper any other. And that, I think, sets us apart in a big way from a viability standpoint or a solutions ideal standpoint. Also, the data node is a point of reception that is also responsible for Snapshot and that incremental change catalog, as well as the repository at a downstream site for everything that's being replicated. And so the hosts are rendered as stateless. And that is really what drives best practices around how this thing is architected, because now the hosts can be literally anything. They could be any size, they could be blades, they could be racks, it doesn't matter. The architecture is kind of cool, and I tried to really simplify this because there's not a lot of moving pieces and parts here. It's very elegant. Under the covers at a software level, it is really involved. And one of the questions that we would often get in our first year shipping product was, why hasn't anybody done this before? And the answer was honestly, because it's really hard. These are not easy things to do. What enables us to do what we've done is the x86 compute and being able to drive workloads that are not only performant, but handling all services simultaneously. In other words, when you see a Datrium cluster, it is doing encryption probably. It is doing deduplication and compression in real time. It's doing erasure coding. These are not optional things that you turn on and expect to degrade in performance. They're always on and performance is still good.
And they're not things that were added later in the life cycle of the product. They were added at inception.
Literally Gen 1, exactly. So if you kind of glance at the architecture here in reference, there are the compute nodes. Now those could be, again, any third-party server. They could be servers that they are buying from us and DVX compute nodes that they are responsible for basically read caching and performance I/O using the compute that's there. And that compute that we're essentially borrowing is only the idle compute that was otherwise sitting there doing nothing. And that's something that that seems to really be a bit of a mystery to a lot of the people that look at our technology. They might be running 15 to 25% CPU utilized, and so there's 75% idle there for us to play with. Well, we'll come in and use a vSphere installation bundle and deploy our software running in user world mode and basically borrow 20% of that idle. And with that, be able to do a lot. Be able to do all of those services simultaneously. So really, regardless if it's a third-party node or if it's a node from us, you have some capability there. The data node is handling all the protected copies of the data. And the data node is designed to scale because it is a global namespace. It's a single namespace that is shared across all the hosts that are attached to it. It is providing global deduplication using a fingerprint comparator methodology where the compute nodes are pre-calculating a fingerprint of data that is being written to the data node, and it simply has to evaluate the fingerprints versus doing some massive, very CPU-intensive deduplication process. This means that that data node is really efficient. It's also not really germane to performance in our stack. The data node is just a receiver of writes. It's receiving those writes into NVRAM, and its global job is basically space reclamation after that. Otherwise, it's very quiet. It's just not doing a whole lot. It is designed to scale in capacity, typically anywhere from 60 to about 160 terabytes. It's a 2U chassis, very power efficient. And it's awfully quiet. So as a footprint in the data center, it really drives efficiency. The I/O processing and where performance really comes from is back up to the compute node side. And the host side is where we are leveraging those resources in terms of memory, in terms of 64-bit bus and CPU to do this work. And that work, of course, is handling writes coming in from the guest VMs, compressing those into memory, applying deduplication, applying encryption if that's turned on, and then sending those writes down to the data node. And so that is really a distributed process, but not in terms of distributing data. Every host is handling the I/O for the VMs that are encapsulated within that host.
So there's just a distributed cache, but the canonical copy of the data is back on the data node.
Yeah, great way to look at it. Also, it's important to note that we have engineered a tremendous locality behavior into this, meaning that every single VM is writing into its own VM queues, which means that when those VMs are laid down to disk, they are individually writing their own unique stripes in an address space that allows us to call those up quickly when we do have need to rapidly repopulate cache, for instance. And so there are efficiencies gained by having that isolation that we can go grab exactly the data we need and nothing that we don't. So there is never a worry about painting the cache with stuff that doesn't need to be there or polluting the cache. There's never any concern for arbitrarily capturing stuff in a snapshot as opposed to a LUN-based architecture where that's always a bit of a challenge. When we look at active versus protection, and that's a good segue there, the active capacity really lives in flash on the host. And so sizing for that is pretty simple. We facilitate a certain amount of flash that we know will handle all of the active VMs that are in that host at any given time, and that we are designed to run flash full. So unlike a controller architecture with a finite cache that's very expensive, where you're constantly trying to move stuff out of cache to free up space and age it out and policy base it, we really say, hey gosh, if you're not full, leave it there, because why not? If you have some reference to it later, it's already going to be in cache. This also means that when you do things like vMotions, we can stay cache populated on a source host, and then as that VM might move back, we don't have to repopulate the data. It's already there possibly.
And of course, you're leveraging the fact that flash has dropped in price hugely in the last few years.
Yeah.
So the affordability of large amounts of flash in your servers is much better than it was.
Yeah, that's a good point. And then when you take that into consideration and then amplify the flash capacity by real-time LZ compression and deduplication, yeah, you're looking at flash costs that are well below 25 cents a gigabyte US, and that is a huge enabling characteristic in that instead of the finite flash model, we believe in kind of more of the nuke it from space model. Like, why not cache everything? The cache is plentiful. The other question that often comes up when we get to that point in a customer discussion would be, well, what happens when I run out of flash? And the answer is quite simply, well, you just add more. And the anecdote that a customer shared with us that has really stuck with me is they said, I love Datrium because I'm never more than maybe $1,000 away from fixing what would otherwise be kind of a catastrophic problem with legacy architectures.
And there's a whole generation of products that were built around the idea that your central shared storage was going to be underperforming.
Yeah.
But long-lived.
Right.
And so you had to build a caching product.
Yeah, and buy out ahead of yourself and so on. Hugo makes a very important point, and it's something that we hold near and dear as systems engineers in the field, which is that when you look at Datrium, every compute node, every host is effectively a storage controller. It's a storage I/O processor versus an array, a box at the end of a wire, be that all flash or hybrid or whatever it is. It's basically got a finite amount of I/O that it can produce, and every server you hang off of that, you're slicing up that pie into smaller and smaller pie wedges. And I like pie, so I like bigger pieces of pie.
Large piece.
But ultimately, this is a big shift in the architecture to say that you can have as much compute and as much performance as you want, and that is disaggregated from this box at the end of the wire. That box doesn't matter anymore. The I/O performance is coming from that top end.
And in my head, I think of the compute nodes as being the storage controllers. If I think of it as a controller and disk shelf architecture, the compute node is the controllers, and you have up to 128 of them.
Right.
And then you have these disk shelves, and you can have up to 10 of those.
Right, exactly.
And that's your array.
And it's huge. And with certain customers, I've just kind of taken through the mental math of, well, how many controllers and cores do you typically have within a storage array? Well, there's 2 controllers, and I don't know, maybe there's 12 cores in each one. Great. How many cores do you have in your servers? Oh, like 24. How many servers do you have? Like 50, 60, 300, so I mean, it really kind of changes the game, obviously.
Yeah, and what's the incremental cost for upgrading your storage controller in your array versus buying a new host?
Yeah, exactly. So, that data node really is the protective capacity, and from the standpoint of customer understanding, that's the master copy. That is the truth of the environment. And so it is a resilient hardware platform. It is designed to sustain multiple points of failure ingress that might take other things offline and survive that. So multiple network pathways, auto path failover capability, dual redundant controller architecture, redundant battery backup, redundant power supply, and an auto support methodology with 5-minute interval heartbeat to home and SMTP relay for alerting. So it is designed to be as bulletproof as conceivable, from a box. But that, of course, in a true enterprise deployment, you're going to have replication. You're going to have that data in 2 places physically and be able to sustain a business level building outage and still, run the business. Yeah, exactly. So that's really what that data node is doing. It is a global deduplication entity, and it's important to stress that there is local deduplication happening in the flash cache of each host, and that is germane to the VMs that are on that host. But then with the fingerprinting that's happening there, the data node is allowed to literally compare all data coming in from every host attached and give you that global single namespace. And as you expand the cluster and grow that cluster out to a total of 10 nodes, that is in fact one global data store that's shared by everybody. Yeah. So this is kind of what it looks like. And I'd like to have a reference in here of what the boxes are so people can get a visual for this. We turned on the ability to sell our own compute nodes here about a year ago. And that was a major shift in how the customers perceived us. Initially, there was some frustration that with legacy servers, they might have to shut them off and put flash in them. And that would be a bit disruptive in terms of bringing our solution in.
Capacity reduction before the increase.
Yeah, and so we said, well, hey, what if we had our own compute nodes? And they said, that's great. And then those same customers said, oh, by the way, can I still use our own? And we said, well, yeah, of course you can. But it was the choice, right?
Yeah.
And so there's basically a simplified license per each host that you connect, and that includes every feature that we offer, all aspects of it. There are no core-based or tier-based licensing or capacity or flash licensing. You have a license, you can put it on the biggest server you want or the smallest server you want. It's totally up to you. Those licenses are, of course, transferable, so I can move them from host to host if I decommission an old host. And within a cluster, you can leverage servers that you already had and our compute nodes, and that those are shared resources across a cluster. There's no symmetry required. And that is a fundamental shift in our architecture that is another big one that really deviates from HCI, which is that they don't all have to be the same. They don't have to even be close to the same. You could mix racks and blades and different brands of servers, different ages of servers, all within the same cluster. Now, obviously, there are intelligent combines from a support perspective that, yeah, if I'm on 6.5, they should all be on 6.5. I mean, there's some basics there that are pretty logical and intuitive, I think. That makes sense?
Yeah.
Cool. Let's see here. So I talked about mixed workloads, and this is something that we're particularly good at. In our architecture, there is no east-west traffic between the compute nodes. And so those east-west traffics that you would see within an HCI configuration are typically what send a lot of I/O across the cluster when you have a big application, or what would be referred to as a noisy neighbor problem. For us, all of our write I/O traffic is going directly to NVRAM in a dual distributed mirror write to the data node. What is sent back and forth between the host compute nodes is only ever metadata reference, or in the case of doing something like a vMotion, that you would see some I/O move between host nodes. And it's suffice to say, our caching follows the VM, and that this is a live and dynamic migration. So instead of having to move a VM and wait for cache to warm up and have that be a long time, it's relatively instantaneous, that we are rapidly populating data from the data node into the cache of a destination host. But mixed workloads are really good for us because you have a workload that's satisfied by the host that it's sitting on. And this also brings up another philosophical moment of inflection. If I have a scattering of older servers and I have a scattering of newer servers, and I have an application that suddenly needs more performance, if I move it to the newer, faster servers, it actually goes faster. And that is a deviation from traditional SAN behavior, where I am truly limited by what the controller can output. And if I've reached saturation on the controller, I can move VMs all day long. It doesn't mean anything.
Still I/O bound, no matter where it lands.
So we really do believe in the grass is greener in other pastures. You could use tools like DRS effectively to manage the migration of VMs and balance them across a cluster based on the merits of the host that they're sitting on. That's very empowering to the community that we serve. The customers really seem to dig that. They also know that they might achieve higher VM densities on a newer, faster host. That's all fair game. You can just increase the amount of flash that you have in that host. That really brings me to the concept of speed. We don't talk a lot about performance in terms of our customer communication, because the performance is really inherent to the intuitive nature of flash. If I put flash in the host, it's probably fast. It's probably going to be quick. Latency is going to be low, right?
I experienced this on my laptop.
Yeah, okay, right. These are known things. And yet, when you take that a step further and you recognize, well, gosh, I can continue to add host nodes, you can increase where a host node is a unit of vaulting forward to say, gosh, I have this much performance now. If I add another host node and break the VMs out across that, I'll have double or triple or so on. And it does scale linearly.
Yeah.
Also, we have two modes of operation within the host. And this is kind of lauded. We get a lot of feedback on this because we operate in a mode called fast and a mode called insane. And insane mode gives us the ability to implement a per host control in VMware, to say I can go into an individual compute node and basically bump from fast mode to insane mode, and on the fly we will jump from 20% CPU utilized to about 40. That's a top end limit for us. We won't ever exceed 16 cores, so that's kind of our top end threshold. We will also yield back to VMware, so we're not trespassing, if you will. This is a soft reservation. But it means that I can see latency decrease and I/O double on the host for a workload that needs it. And the anecdote that I'd share is really based on a customer story that the customer said, hey, look, the business came to me after my Datrium implementation and said, we've merged in with another group. We have more employees coming into the fold. We don't have any more money for more infrastructure resource. Can we bring them into what we have? And that customer was running 3 host nodes in fast mode and said, let me go take a look. And he went down and he put 2 of them in insane mode and was able to soak in, it was something like 50 more users, Exchange, a bunch of database stuff, a bunch of back office file server, a couple of big databases, and really no sweat. I mean, just completely like not even thinking about it, and came back to the business and said, we've done it, it's not a problem. I'd like another 20 to 40,000 in the budget for next year for a couple more server nodes, and I'd like a raise. And like that's how easy this should be. And that's really the intent of what Open Converge provides, is saying, look, it's agile. You can just do this stuff. There's no reason not to, and you don't have to go into the data center to do it. It's not recabling something. It's just go look at the software, drop into vSphere that you're using daily, and make a quick change and adapt to something that happened. So that's kind of cool about our stuff. The final thought that I'd have on really setting the tone for disaggregation is that we can populate a customer's environment based on their needs and their focuses as they shift from capacity to performance or blending across those two areas. And that's this concept of split provisioning. And split provisioning is not new to the space. You hear the MSPs talk about this. You hear Google and others talk about this, that we can facilitate growth across the cluster of host compute nodes independent from data nodes. Now, obviously, there are some math norms here that I need at least 4 data nodes to be able to get beyond let's say 64 to 128 compute nodes. I will max out at 128 compute nodes with a 10 data node cluster. I want to emphasize that these are really QA limits at this point.
Right.
And it's really driven by how far customers have pushed us so far. At a file system level, at an architectural level, this will scale way farther. And so these are kind of the lines in the sand that we've gotten to at this stage, having shipping product for coming up on our 3rd year. That with some of the testing that we've done, we know exactly what we can expect from the resources the customer inventories to us. Right. We know exactly what to expect from the compute nodes that we put out there and what the data nodes can do. And it's kind of cool to be in that position, honestly, because there's nothing that we have to worry about. There's nothing that stresses us about, well, gosh, if they have this workload and this kind of server, it's going to fall down. There just aren't those kinds of things present here. It's a very different architecture, and that leans on that software-defined modality to say, yeah, I can build it however I want to. Does that make sense?
Yeah. It's a very cool structure.
So it would be important to round out some of the detailed things in terms of what we do with this architecture and some conveniences that we built into it. And a big one seems to be encryption. A lot of our customers have had mandates for encryption dating back several years. They are just now getting to a point where they're delivering on those promises to the business. We are a big part of that. In fact, several of our customer engagements through our partner reseller community have been born of just the need to encrypt. And oh, by the way, we do all this other stuff too. And so that's how some of our projects have even gotten going. We have deployed what we call blanket encryption. So as we referred a lot to the host compute side, one of the things we take advantage of is that in any server that's x86 that dates back even, let's say, 5 years old, we have advantage of the AES-NI instruction set. And so we can switch that on, and with minimal overhead, literally encrypt everything from the guest VM all the way into Flash, all the way down the network into the data node, and in fact then use TLS 1.1 and 1.2 compliant encryption over the wire to replicate that data. Yeah, and then of course it's encrypted over there as well. So this is, in the cluster, 256-bit TKS, and we're working on our FIPS 140 cert through third parties, so we should have that in a matter of weeks, but otherwise it's compliant. And to turn it on, it is almost one of the most boring things that you can do within the interface. I mean, it's literally like, okay, encryption, go, and everything is encrypted, and it's just there running in the background. For sake of folks looking at this and in reference, it is pretty typical that we are less than 3% overhead to do that, to have that encryption on for literally everything in the entire cluster. Yeah, I mean, it's pretty straightforward. The blanket encryption gives us a lot of latitude to protect an environment. It's also worth noting that if you lose the password because you lost the Post-it note under your keyboard, we don't have any way to get you back in there. That data is truly encrypted.
Real strong crypto. Self-owned key.
Yeah, exactly. I mean, you're not getting at that. We use built-in key management. We will probably look at focusing on some third-party key management capabilities next year. Right now, that key is all internal to us, so there's nothing extra to manage. We're not using self-encrypting drives, any of that kind of stuff. I mean, this is truly end-to-end blanket encryption. Snapshot methodology is really pretty slick because our solution focuses on, again, being the primary active data and also your master backup, your copy of this data. And snapshots are how we facilitate that. Snapshots that we use are, of course, focused on really metadata manipulation, as all advanced snapshots are, that I'm not copying a bunch of data around. They are incredibly granular. So I have the capability to snapshot at a per VM level and even at a file level underneath VMs. To define that further, I don't mean granular file recovery. I don't mean exchange recovery, mailbox level. What I mean to say is that, yeah, we have our own VSS provider that we wrote. We can protect those applications. We can protect all the way down to granular vDisk or VMDK and containers, and that we have implemented a full catalog infrastructure to go and search that stuff, that you have that context to go recover. anything that we snapshot, we can also replicate. Anything that we snapshot, we can clone, that we can restore from. Zero-copy clone, of course, is also a core function of our copy data management. The intelligence behind Snapshot is driven by what we call protection groups. And protection groups are very similar to traditional backup policies that I would define VMs by naming convention, by search string convention, by wildcards, and have them be included within protection groups, and then define schedules, define whether or not they're replicated, and even define if they're replicated within platform, if they're replicated off platform to AWS, because we support that as well. So it really is, again, very agile and granular, that I have visibility from the file level through the VM, through a group of VMs, all the way to even providing site-to-site level recovery, because the replication is really built upon a cloud foundation. The cloud foundation is depicted in that we have two organizational constructs. There is the data store that everybody's familiar with in a VMware context, that I can go in there and I can browse VMs and do stuff with them. And then there is this new context of a construct of a snap store. And that snap store allows me to go in and browse any of the snapshots that are there, manipulate them, and be able to do that without any interference to anything else going on within the cluster. So restoration out of order, or deletion out of order, or cloning, these are all atomic actions that don't have any negative impact on anything else. This also means that because of that organizational unit being in the snap store, I can go review that history and pick a point in time and recover from it. And then, of course, if I've set up replication, I can do that at either end. Now, there are some intuitive things from this that are not immediately obvious to everybody that looks at this for the first time. The first is that I can have dissimilar retention depth. Doesn't sound like a big deal, but I find when I talk to customers, everybody assumes I have to have the same thing at both ends. Well, you really don't, and there really shouldn't be a need to do that anymore. I would love for a secondary site for DR to be about 1/3 the cost of the primary site. And why not? If I can have more white box resources down there instead of brand name servers, sure. If I can have a physical footprint of the data down there that only pertains to, let's say, a week's retention, because that's all I need for DR, versus 6 months of retention over here.
Because I've got compliance requirements to set aside over there.
So, why not have dissimilar capabilities? And that's what we absolutely support. So that's something that we do tend to talk about with our customers. And when we do, they're like, oh, cool. That's, it's just a neat thing. But that capability also then to replicate really in any direction, many to one, one to many, bidirectional cross replication, and then even to branch off into AWS for the ability to stage and recover.
Low cost retention.
Yeah, exactly. The customers that I see on a daily basis will frequently ask me, hey, if I don't have a secondary site, what are my options? Now, we really believe in the partner ecosystem, in that there are technologies that do certain things that we just don't do. And so if a customer says, hey, I got a primary site, but I don't have a secondary site, AWS comes into play, and that makes a lot of sense. If they have a secondary site, but they don't have budget to put Datrium in both places, but they already have license to, let's say, Veeam, well, absolutely, Veeam has replication built in. You could replicate that to a completely dissimilar infrastructure over there and be able to recover that without Datrium being present or a part of that. So it's important to denote that within the foundation of our architecture is an intent to not lock in, to not have imposed restrictions, that you remain open to the customer's solution ideal and really to what their business needs are.
Nice.
Yeah. So that's Datrium architecture.
Excellent. Well, that was a lot of Datrium architecture, and we will have more Datrium internals and some deep dives into particularly the I/O performance and data write, and some really interesting failure mode stuff as well. So,
cool.
Thank you very much, Devin.
I appreciate it. It was really a good time. Thanks for great questions.
And we'll see you on some more of the vBrownBag Build Day videos.